Okay, we're going to be talking about the states or phases of matter. So the first thing that we need to talk about is energy's effect on matter. So we're going to define energy as the ability to do work or to cause a change. So when matter has energy, it's moving, even if you can't see it. So even something that doesn't look like it's moving at all, if you were to be able to look at the molecules and the atoms that make up that substance, you would be able to see that they are moving. The only time that matter is not moving is when it's at a temperature of absolute zero, which is negative 273.15 degrees Celsius or negative 459 degrees Fahrenheit. And that's the theoretical point at which all energy is taken away from matter. So if you were able to take something and you were able to freeze it and get it down to this absolute zero, you would, in theory, there would be no energy in that object. So temperature is actually a measurement of the motion of the matter. Okay, so we always think of temperature as just whether it's too hot or too cold, or in our case, as it's been recently, how very, very cold it is. But it's actually a measurement of the motion of the matter. So if you have low movement, okay, so stuff is not moving around very much, you have a low temperature. So when it's been, the negative 20 degrees that we've had outside over the last couple weeks, that's a very low temperature. So anything that is that temperature, everything outside, there's not a lot of movement going on. In the summer, okay, when we have a high temperature, so when we're getting into 80, 90 degrees, there's a lot of movement, so there's a high movement. So low temperature, low movement, high temperature, high movement. So how do we measure the energy of matter? Again, we use temperature. Typically, you'll see a thermometer. We use the Celsius scale. So water is boiling at 100 degrees Celsius. In Fahrenheit, that's 212 degrees. Water freezes at 32 degrees Fahrenheit, or 0 degrees Celsius. And the Celsius scale was named after the Swedish astronomer Anders Celsius. Okay. It's commonly used around the world, but we use the Fahrenheit scale. But in science, we'll be using the Celsius scale. And it's based on the boiling and freezing points of water, and then it's divided by 100. So again, we have that factor of 10, just like in the metric system, which is why we use it in science, because it's easier to work with. So you can remember it this way. When it's 0, it's freezing. When it's 10, it's not. When it's 20, it's warm. When it's 30, it's hot. Because if you look here, right, we don't have 30 on here, but we have 37 degrees Celsius, and that's almost 98.6 degrees Fahrenheit. Okay, so that is a great deal of warmth. Okay, so you're probably commonly familiar with the 3 main states of matter, which is solid, liquids, and gas. There are actually 5. There's also plasma. And in plasma is somewhat common. It's difficult to maintain. Things like fluorescent light bulbs or signs made out of noble gases, like a neon sign, like if you ever see in a store, like typically that open sign is a neon sign, and that's in a plasma state. And that is a higher energy level than a gas. And then for our 3 common states of matter, gases have a higher energy level, liquids are more in the middle, solids are the lower energy level. And then we have what's called a Bose-Einstein condensate, and that's lower than a solid. And so the clumping of the atoms are at really low temperatures, so they're not moving around a whole lot. And these are formed at temperatures that are close to that absolute 0 that we talked about. So if you're looking on an energy scale, right, you've got Bose-Einstein condensate, then you move to solid, then you move to liquid, then you move to gas, then you move to plasma. So you go from low to high. And you can see the arrow here. So the energy difference in the states of matter. In a gas, and matter has more energy to move around. So you can see in a container, the gases, those molecules are going to spread out. Okay, they're going to fill the container. So they're moving around, they're going to fill the container. If this container was open, these gas molecules would be coming out the top of the container. So in a liquid, okay, this is going to move around more, or less than the gas, but more than the solid. So you can see they're spread out a little bit more. They fill the bottom of the container. They take on the shape of the container when it's in a liquid. So if I were to pour this into a thinner glass, right, it would still take that shape. If I was to pour it into a wider glass, oops, sorry about that, it would take on that shape. The molecules would spread out to fill this container. Your solid, see those molecules, they're closer together. They have less energy to move around. So they're still moving around, but not a whole ton. They maintain their shape. So it doesn't matter what the container looks like that you put them in, it's going to take on the same, it's going to keep the same shape. So this has more, over here this has less. So we're talking about shape and volume, and this is really, really important, guys, for states of matter. This is what I really want you to know. So definitely make sure that you write this down. You might even want to put this visual in your notes. So for a solid, it holds the shape. Okay, so it keeps its shape no matter what the container looks like, and it has a fixed volume. So remember we said that a volume is the amount of space that it takes up. So a solid, no matter what container you put it in, it's going to keep the same shape, and it's going to take up the same amount of space. Okay. The liquid, okay, which is in the middle, takes on the shape of the container, and it maintains the same volume. So it takes up the same amount of space no matter what size of the container it is, but it's going to take on the shape of the container. So if you were to pour this liquid into a smaller container, the liquid would be higher. Okay, and that's how it keeps the same volume. If you were to put it into a larger container, right, the volume, the level of the liquid would be less, and so that's how it keeps the same volume. Your gas over here, it keeps the shape of the container, takes the shape of the container, so it's going to, again, it's going to fill that space. Those molecules are all spread apart. No matter how big your container is, it's going to fill it. So it not only takes the shape of the container, it also takes on the volume of the container. And again, if this was an open container, you would see gas molecules escaping out of the top of the container. Okay? So again, solid holds its shape, it has a fixed volume. So same shape, same volume. Okay? A liquid, it takes the shape of the container, and it has a fixed volume. So different shape, same volume. Your gas takes the shape of the container and the volume of the container. So different shape, different volume. Okay? Make sure you go to Edmodo and take the Edmodo quiz.